Without further ado, I want to introduce a really great first keynote. It makes sense we're kicking off ConnectX with Satya Yadav, who's truly on the cutting edge of connectivity. He's a global head of IoT ecosystem development at Amazon Web Services. He's leading their efforts to harness edge computing to power everything from machines that learn to cars that drive themselves. And there's a huge opportunity for everybody in the infrastructure industry with all these edge data centers, and Amazon is sort of leading the way. So please welcome Satya Yadav.
Good morning. How's everyone? Thanks, Jonathan, for the introduction. We all live on the edge of some networks. Our homes are edge of, you can call them roadway networks. Home gateway that you have in your home is the edge of internet. Hospitals, clinics that you may be accessing as edge of healthcare networks. You can think of many other examples. For example, transportation, energy, manufacturing. These are all some kind of networks that we access on a daily basis. And if you think of technological advances over the years that we have seen, made it easier to access these networks. And I'll give an example that we all familiar with. Imagine having a day without smartphone, right? That is your access to the internet. And so how far we have come along in terms of technological improvement in the way we access the network. Now the question is, we as an industry, what kinds of improvements we want to drive to improve our life on the edge, if you will. I would say these billions of connected devices that are either some of them are online already or going to come will help us live longer and healthier life, help us take care of our precious resources like energy and water and distribute them in more efficiently. Our cities, much nicer place to live, safer. So the question is, what advancement that we can expect in future and together as an industry to make that happen. So before we go there, I wanted to do a very brief history of computing. And as you know, computing industry has tremendous impact on our lives and how our lives have improved over the years. Commercial computing started somewhere in the 1950s as mainframes. These computers were housed in a centralized location, and if you were to access them, you have to go to that building to access it. I personally started my computing journey by writing my first Fortran program in a computer called PDP-11. Things did not change for a couple of decades, and then largely these systems were used for solving scientific problems, weather forecasting, large compute problems, mostly in the universities on our government agencies. Then microprocessors were invented, and my previous employer, Intel Corporation, drove the revolution through what we called it Moore's Law, named after one of the founders. And what it said is computing or the microprocessors will pack twice as much circuit and cost half as much every 18 months. And that led to a complete revolution in terms of what applications we were able to access or develop or make it available to the consumer. But more importantly to me is it also drove changes to a number of other technology, analog technologies. Think of music, video, photography. And with the very cost-effective compute, these problems can be reframed into compute problem, and these industries, analog industries, were transformed. As you can imagine today, all these things are packed can be put in the pocket and much more, multiple wireless technologies, for example. They all could fit in. What that meant is, along with 4G that made the access much faster, what it meant is all of us wanted these internet services anywhere, anytime. And that led to another revolution, again, a kind of pendulum swing back to centralized. And to run these services, you needed elastic compute, storage, and faster network like 4G. So where I work now is AWS. This way we have enabled these much more economically to all sorts of customers. So think about Lyft, Uber, or Airbnb, or any other favorite service that you access today would not have been possible without these data centers or public data centers, what we call them cloud, that made it possible for startups and any number of customers to access the same amount of capability in the compute than the previously only available to the large organizations. Now the question is, where do we go from here? And it seems to me the pendulum swings back again. I started my comment around the billions of connected devices. So in industry, we call it edge computing, fog computing, or edge cloud. You can give any number of names, but the question is what it is that we are enabled in terms of the technological growth that fuel the future for the next set of revolution. I started defining the edge as from the consumer's perspective, but you can think of cloud or centralized resources or the core of internet as the center of these networks. Then you can define point of presence as one of the edge, where these compute and storage resources are typically connected through a private high-speed link back to the cloud, for example, and in Amazon we call them availability zones. Think of wireless infrastructure, the compute today and storage today typically used for telcos their own use. Can these be expanded through what's called 5G and then innovation through what's called multi-access edge computing that you are familiar with, what's possible there, and that you can define edge there. Racks of servers in the mining or office building or somewhere else that could be providing the compute, you can call that an edge. Lots of compute that today on the cars, aeroplanes, or anything that's moving, that could be qualified as an edge. Your home gateway or IoT gateways for the factories could be an edge. And finally, all the end nodes could also be edge. So depending on which view you take, you potentially could define the edge in your own way. And the reason I'm using this to make this point is there are different use cases. Different edge computing use cases drive different understanding of what you mean by edge. But the use cases today, as you know, the compute does exist in any of the examples that I'm showing here. Compute is there today. It's not that the compute doesn't happen. My point is the compute happens in a more discontinuous way, meaning there is no continuity, or these devices that are put from the day one to the day it was taken out of service, they do not change. Their action do not change. So if you were to drive improvements, and if you were to make new things happen, then these computing services have to be what I call, needs to become intelligent computing. So same use cases that I was showing previously, but superimposed certain things. For example, in the industrial case, think about detecting anomaly or predictively maintaining all the equipments, or if it's a finished good, at the time of production, immediately knowing what the quality of the goods are. Think about in the transportation, avoiding collision is a real-time action needs to happen. It can't wait for sending all the data back to the cloud and back to determine that question. You can take any number of examples. One of my favorite examples is think about a security camera on a city street. It is a camera, and you can think it can detect the traffic patterns or disturbance, but it can do a lot more things when you apply the machine learning to it. For example, it can detect what other city services you need to do. If the trash cans are lined up in the view, it can detect when the trash can is full. You don't have to put any more sensors to it. So if you apply these intelligence to these use cases, you could see that over time, the same use cases could improve because the systems are learning and changing their behavior. Now, what factors should we consider as we think about designing these systems that are distributed systems that you decide where to process the data or where you actually apply different logics? Obviously, cost will be a major factor in deciding scalability of the system would be factor. I simplify the diagram here to say there is a cloud and an edge. So the first principle is I gave you an example of some real-time applications. So speed of light is constant. So the distance from the source of the data that you want to process and where you want to process will dictate how fast you could respond to. Second factors to consider is the cost of the data, transportation or cost of, not every data is the same value. So which data you would want to transport to the cloud or which data you want to process locally. Government regulations, privacy regulations like HIPAA, which dictates how our healthcare data is dealt with, or GDPR is a privacy regulation that's being implemented in Europe. So these will dictate, other boundaries to what you want to do. And finally, to make this work, you need to think of consistent programming model. One of the difficulties we have today, the embedded systems are built to run for a number of years as an independent entity, as I described, discontinuous fashion. In order to make this thing happen and make this thing work in an intelligent fashion that I'm envisioning, there has to be a programming model that we could apply across from the edge to the cloud. So what can we apply from the cloud? There are a few examples, not exhaustive list, but I'll give you a few things to take away, how to think about the edge computing evolving. So the cloud computing is built on a big notion called virtualization, which virtualizing the machine, making it available for multiple applications, making it available for multiple users. That created the elasticity of the compute. Also the network resources, as we know, as the network grew, you can think of how to use the virtualization into the bigger context where the cloud and the edge and the network in between come together. And then industry, you're part of it, is something called network function virtualization is an example. The other key ingredient that comes out of the number of advancement in the cloud technologies, how to distribute computing and manage the life cycle. So the container technologies and container management technologies made it possible to deploy these things in scale. And now you can extend that technology to deploying it scale in remote locations, if you will. And then finally, I hinted on the deep learning and machine learning. Today, it's dominated in the cloud. It requires quite a bit of resources. But advances in computing I spoke about makes it possible for the neural networks and then some of the accelerators that are available in the cloud to also available on the edge. So we use these principles. So I want to briefly say, okay, what can you do today? I talked about technology advances and I talk about how you can apply. So this is one of the services that are offered by my group. It's called AWS Greengrass. This is our edge computing platform. And then the idea is that extending AWS services that some of our customers are using in the cloud make the same services available to run on their connected devices. That happens to be IoT gateway or racks of servers. These capabilities that listed here are more driven from IoT, but things like having a common programming language or common programming model makes it easier to program these number of devices, keeping them up to date. I'll talk about machine learning in a minute. Having access to modern programming languages, where the programmers who have learned to develop applications in the cloud, how can you transfer those applications simply? So we have a programming model in the cloud called Lambda. It's an event-driven programming model. What it means to you is if you don't have to a priori predict what the demand of your service would be, and if you use the Lambda programming model, it scales depending on the access request to your service. And so so now imagine that service that you develop in the cloud, and then you can run it on your connected device using Greengrass platform. I want to spend a minute on the machine learning. So I mentioned that to do the data, training the models requires enormous compute resources. Today, any of the examples that you know, and all of you are being touched by this artificial intelligence or machine learning in the cloud every day. Any application that you use, whether it's the recommendation on movies or products, your preference, the ads that are shown to you, they're all driven by the machine learning and intelligence in the cloud. So the training of some of the things that we know still requires quite a bit of compute resources and capability, and so it's suited to do that in the cloud. But one of the things that Greengrass does is lets you take the trained model either using one of our services called SageMaker, or the models could be trained somewhere else in some other fashion. But using the Greengrass backend service from the cloud, you could deploy the same model to any number of Greengrass aware devices or Greengrass core devices. The way to do this is these devices are capable of running these machine learning models or inferring based on these models. And today, with the improvement in computing, specifically improvement in computing more specialized for running machine learning capabilities, that are becoming much easier to put into the smaller devices all the way to the sensors. So think about these capabilities. I talked about the video camera example that are connected, all running Greengrass. Then you can easily deploy them to any number of these services. And then the goal is that you are processing the data and taking the action immediately. Now you can extend this to any number of applications. You can extend to predictively determine the uses of your network, predictively determine what the capability you need. So you could scale resources up in advance of the new use cases that you may be predicting. Now, want to end with a note with showing that I mostly focus on the edge. But in terms of how these things fit together from the edge to the cloud, then a few other things I wanted to point out. So Greengrass is our edge computing platform, but we do have a product called Amazon FreeRTOS that is a IoT operating system for microcontroller-based units. So on the edge, you can use these devices to connect to locally to Greengrass, and then Greengrass brings the local intelligence to these devices. So you can make those decisions and implementation locally. One of the key aspects of our edge computing is it should be resilient to network disruption. So the system should continue to run even if you lose the connectivity. I did not go into the details of how we keep the state sync. So one of the capabilities of the Greengrass is it keeps the state of the local machine in sync with the cloud automatically. And if you lose connectivity, it'll bring it back. To give an example, one of our customers used Greengrass in mining site on these running on trucks, calculating or gathering the data, how rough the road is, using the vibration data. And this gets processed locally on the mining site using the servers running on the mine. And when the cloud connectivity is available back, that this gets synced with other mines. So this gives them the flexibility how they want to run these. We also have one of our partners uses the Greengrass to implement multi-access edge computing on their networking gear for the telcos. And the advantage is that new functions could be sent to these devices at any point. And then in the center, we have set of cloud services, starting with the IoT focus that's listed here, IoT core, device management, security service called Device Defender, and analysis. And behind that, we have 100+ different services that it connects. So now depending on what application you're trying to build for the edge, you can put these things end to end. And of course, we have set of partners. Not everything that we do is complete solution. So we provide building blocks, and a number of our partners from hardware to software, they help us complete the picture. So with that, the examples I started with, we believe it's those applications can be built today. All right. I know I had limited time today, and I rushed through some of the content. So if you have questions, my email is listed on the back. Feel free to send me any questions. And thanks for your time.